Hello, and welcome to this short introduction to Honeychrome. I'm Samson from the cytometry project. Honeychrome is open source, cross-platform cytometry software for data analysis and acquisition. It's part of the CytKit project to make an open source cytometer. Honeychrome, however, is not just for acquiring data from a CytKit, but for analyzing FCS files from any cytometer. After you install, you start the program and you'll see a splash screen like this. It does light mode and dark mode. I prefer dark mode personally. This is on Linux, but it looks pretty much the same on Windows. And I scaled the screen and made my mouse pointer big to make it easier to follow on a screencast. But you'd probably use Honeychrome on a much larger monitor with much more space to see cytometry plots. So I'll show you a few examples to show you how to use it. I'll create a new experiment. I'll call this HSC data and save that. The experiment holds a set of samples, channels, gates, cytometry plots that can be applied to any sample, and a spectral model that converts the raw data into unmixed data. So you see these three tabs. Raw data is just what the instrument measured. Spectral process will be the list of controls or the assignment of channels if it's conventional cytometry. And then the unmixed data, once you've defined the spectral process, will show your fluorophores that you'll do your cytometry on. Now it's important to understand your workflow here is spectral, even if you're using it to analyze conventional cytometry FCS files, which is quite simple, as you'll see in a moment. So don't treat the fluorescence channels, that's these here that the instrument measured, don't treat them as interchangeable with the fluorophores. You need to define the spectral process that defines the relationship between the two. Now I'll give a couple of examples. Firstly, I'll import some FCS files from another instrument. So that consists of moving the FCS files into this experiment's raw data folder. I'll open it up there. I'll move in some FCS files, so a sample file and some single stain controls. Close that again. And the second step is to update the experiment configurations. So this experiment file has to have its list of channels and channel ranges set to match the FCS files. So I press this button, it reads those automatically and says what it's important. So now it's refreshed, and you can see the single stain controls and the sample that we've given it. Let's click on it to browse, and first thing you can see is on the raw data the channel ranges which are from the instrument it was imported from don't match the data. So you can right click on that, fit axes to data, do that for both the morphology plots, and move around these default gates so that they reflect the data. I'll scroll down so you can see the raw data, the ribbon plot, the single channel histograms, and see it also for the controls. These are bead controls, as you can see, and you can also see a gating hierarchy on the right, which we can hide actually, since we're not going to use that. Now, the next thing to do is to define the spectral process. I'll change that tab, and now there's some help, a description of the spectral process and how to use it, but I won't go through that now. The main button here is this, auto-generate spectral controls. If you've got a list of spectral controls under single stain controls and you've named them according to the label, Better even if you put cells or beads in the name, so it recognizes whether they're cells or beads. Then you press this button, auto-generate spectral controls, and you can see now the profiles, the spectral profiles for each of those labels. So there's APC, AF488 and PE across my very limited spectrum there from a conventional cytometer. You can scroll down further, you see similarity matrix. These are not similar, these are well assigned to separate fluorescence channels. An unmixing matrix, as you'd expect, they're dominated. Each label is dominated, or each channel is dominated by a single fluorescent marker. There's also spillover or fine-tuning matrix. If you want to edit that, you can double-click to edit, or you can roll the mouse wheel. And end-by-end plots. So for any of these samples, you can click on them and see end-by-end plots, and you can also roll the mouse wheel on this. So if you want to do any fine-tuning, so you can see, roll it up and down, and it adjusts. It can also be gated to any of the gates in the unmixed data. So I'm happy with that. I will go to unmixed data. It copies by default all the plots and gates from all the morphology, all the non-fluorescence plots and gates from the raw data. So you can use the same cells and singlets gates, for example, and then define new ones. So I'm going to define a new plot from the singlets. You can change the parent gate there, change the gates on the axes, and put in a let's take a polygon gate. I'm going to gate this sample here, and let's call that HSCs. Double click to edit. OK. I'll create a new plot from that, and let's just change one of these to CD45 and put a rectangle gate on that. HSC more, right. You can see on the right the gating hierarchy shown and hidden with this button, and you can also move these plots around. So you can move that, for example, to the front, to the back, move it left and right in the order. You can double, if these are too small to manipulate, you can double click, and you can see you can shift the axes, pop this back in, or say on this one, on the logical plot, you can adjust by just dragging both the linear region at the bottom or the logarithmic region around the top. I can export analysis of the whole thing, including the spectral process. I'll press that button. It exports a file in docx format, which is convenient if you want to open the file browser and go back to it. It's convenient if you want to cut and paste, for example, figures, the individual figures, or the table of the gating hierarchy and statistics, and it also puts in there by default the spectral model, the labels, the profiles, similarity matrix, unmixing matrix, spillover, end-by-end plots. You can also export individual images or copy them to the clipboard. Next, I'll give an example of using Honeychrome to do conventional cytometry with manual compensation. So I'll make a new experiment. Let's call this T-regs, no controls. This time I'm going to import a few FCS files, all about T-regs, but no single stain controls. So close the file browser and press Update Experiment Configuration. It said it was successful. Press OK, and now I'll browse those. There we go. Again, right click and on the appropriate plots and fit axes to data. This one has a width rather than a height for the singlets plot. You can see the ribbon plot. This is conventional cytometry. There are only a few channels. So this time I want to analyze those. And instead of using controls, I'm going to assign fluorophores to each channel. I press this button, auto-generate spectral controls, and it'll say you have no spectral controls defined. Do you wish to assign fluorophore names to all your raw FCS channels? You can then edit the name. So I'll say but yes. There we go. So each there are 4 channels and 4 labels in this case. I can delete any if there are any extra. Control type is now channel assignment, which means that we just have a delta function in the profile. It's 0 everywhere except for the one that the label is assigned to. And I'll edit this. Now it was CD4 bit C in label FL1, CD127 FL4. You can select them one by one, see their profiles. Select none or select all shows everything together. Similarity matrix is 0 off the diagonal because they're all just delta functions. Unmixing matrix is just a unit matrix. This time we're going to do manual spillover. So it starts out with the spillover being 0, and to compensate, well, just look at it, and this is the fit C against P, for example. Roll the mouse wheel, roll it some more until it looks about right. So that's about 12% 12% compensation between fit C spilling over into PE, as they say there. And if you want to look at it, filter the rows, you can say look at the just the PE row, and there you go. That's just the row off the n by n plots, and row of the spillover matrix. Makes it easier to track what you're doing. So I'm happy with that. I'll go to unmixed data, and I'll create a new plot from my singlets gate. I'll look at CD3 against CD4 first, and gate my I'll double click to expand that. Gate my CD4 cells, and pop that back in. New plot from that gate, and put CD25 against CD127. Yes, I've missed the main cells there. Let's edit it all. Let's just change that. Right, and then that's what we're supposed to. That's what we're supposed to see there is this. Those are the T-regs, the CD25 high, CD127 low. I'll manipulate this this gate to shrink the linear region a bit so we can see them more clearly. and push that out a bit. Now I'll set up a gate around the T-regs there. Okay, pop that back in. I'm satisfied with that, and we'll look at the gating hierarchy. The T-regs are 6% of the parent gates, about 2% of all events. So that's all about right. So next I'm going to just look at some real spectral data. And import this time the single stain controls are in reference group under set 1, so I won't bother moving them across. I'll show you how you can set it separately. Update the experiment configuration. Now you can see all these samples we've imported. A whole set of single stain controls as well as other things, but they are not in there, so we've got to fix that first. Go to edit experiment settings, and this line has to point to your single stain controls wherever they may be. This is all within the raw data, so I'm going to put a raw set 1 reference group and press OK. So now they're in the right place, and we can have a look at them. Very good. That's the fully stained sample there. I'll just adjust my morphology gates. I'm going to define now unstained positive and negative instead of using the internal positive and negative for each control. To do that, I'm going to define a new morphology plot and put, say, well, let's pop it out to make it easier, and the unstained negative will just be these, or sorry, it has to be marked neg, has to be marked neg unstained, and unstained positive I will mark all the roughly bigger cells like say a pos unstained, because those are the ones that will dominate the autofluorescence. Okay, so pop that back in, and now in the spectral process, before I click the Auto Generate Spectral Controls button, I will tell it to use the unstained negative, and it will find those gates. And off we go. It will go through the full set of single stain controls. Calculate all the histograms there of the n by n matrix. They're quite a lot now. Now you can scroll down. Firstly, see there are a lot of controls. Some of them are very similar. Similarity matrix. Look, you can see there's a whole lot that are actually pretty much identical. Actually, that's because there are some beads and cells with the same fluorophore in this control data set. So we'll have to fix those. Get rid of the unnecessary ones. It's quite can be quite overwhelming to do this for a large panel. So I'll do a couple things to make it easier. I'll go to App Configuration and make the n by n plot size smaller, say 100. OK. And now on the spectral process, if I go down to them, they're smaller. I'll load up some of these to have a look. I'll also get rid of the duplicate controls. So see this one, these two are the same. If I can hold down Control, select two at once, you see that they have the same. First, they have the same name, have pretty much the same profile, and are identical. So the OLS algorithm here is trying to pick out an infinitesimal difference between the two to give separate fluorophores, which is not correct. So I'll select all the duplicate ones and delete them. Yes. And now the similarity matrix looks better. There are a couple that overlap quite a lot. I mean, the unstained overlaps a lot with this BUV 805. But now, if I look at the controls, you see they look sensible. If I look at the fully stained sample, it looks about right. And another thing I could do without redefining, recalculate it if I've moved my, for example, my definitions of the unstained gates. If I go back to raw data, you can see now all the plots and gates that it's using to define the if we go back to raw data now, you can see all the gates that it's using to define the controls, and among them is the one that I defined myself, the positive and negative unstained. If I, for example, move this across a bit to just the biggest cells there, I can go back to spectral model editor and recalculate, and you'll see it's now a slightly different profile for unstained, and also the negative used for all the others will be slightly different. Another thing I might want to do is inspect these line by line, so I can go through and look at the labels, look at the relevant lines of the similarity matrix, the unmixing matrix, spillover matrix, and n by n plots. If I load a sample there, I can filter those, say, by singlets, and if there's anything wrong with any of them, if there's anything obviously wrong, I can compare these with what I've recorded before, what I've got in my library database on my system of the same label. So I'll have a look at those. You see there are a couple of copies there, and I could load that one, say. So select all, or select none to inspect the n by n plot again, and that looks about right. I can, if there's any that I'm concerned about, I can do fine-tuning by rolling the mouse button, highlight that, select that, just that control, and move this one a bit by rolling the mouse wheel. Now, go to my unmixed data. It's copied the non-fluorescence plots and gates automatically. Delete that gate, that's this button here. You can add plots with this button. So for example, if I want to look at viability, that the viability marker against count for a 1D histogram, say, and use a range gate for the viable cells. And get that off singlets. See, they're pretty much all viable. I can define some new plots. I can define some new plots. So, for example, we could look at CD11 against CD45, and use any of these gates: rectangle, polygon, ellipse, or quadrant. Let's try quadrant for a change. You can see the new gates in the gating hierarchy. I can move around the order of these plots. I can click to select them and move them back and forth, change the order of the plots, move them to the front and the back. I can use any of these gates, and I can add new plots where appropriate. So I can add, say, the CD3 against CD11, and put in another kind of gate, so rectangle gate, or put in some more gates, polygon gate, ellipse gate, manipulate the transforms, change the parent gate, having set all that analysis up, I can export the unmixed FCS files if I wish to save those or analyze them on some other system. So press that button and say I want to export only the fully stained set there. Proceed. It will calculate the relevant samples, and you can find them in unmixed in the corresponding folder there. I can also generate a report, and this time it'll add all the unmixed cytometry as well as a spectral model. I can browse to it and open it. Here's the export. And finally, I'll show you the statistical functions to compare samples. So they're on the last tab here, statistics. You can, for example, choose these stained samples to compare in a bar chart. Let's have a look at the double positive and the percentage of the parent. Click calculate, and there we go, a bar chart. You can export that graphic as a PNG file, export the CSV data that's been created if you want to plot it separately in some other software. Since we've got here several FCS files grouped into folders, we could treat those as repeats of a category and do a box and whisker chart. So I'll select now the parent folder of all of those and select box and whisker, and this time let's look at, say, singlets and the mean intensity in some channel, and calculate. It'll crunch the numbers, and there we go. In that fluorophore, there's one sample in the reference group that has it, and the stained samples all match that to some extent, but not the fixatives and not the unstained. Thank you very much. I hope this was a enjoyable introduction, and let me know your feedback.